Hello and welcome back to Ready to Derive. In this lesson, we will be exploring one-sided limits and their usefulness in establishing the existence of a limit of a function at a point. We will use a variety of practice problems to help reinforce the concept. Hope you enjoy.
Let's begin by revisiting the function we were looking at in the last video. And as we recall, there's a hole at x equals 1, and here's a table of values to help us along. So we're going to break down the limit concept into two separate limits, the left-hand limit and the right-hand limit. So we are actually looking at what's happening as we approach x equals 1. And when we think about the left-hand limit, we think about hopping onto the curve to the left of x equals 1 and imagining what happens, or not imagining, seeing what happens to our y value as our x value approaches 1 from the left. So as you can see, we're moving up the curve, and as we approach, as x approaches 1, clearly y approaches, our y coordinate approaches 2. Once again, you can see that in the table. As our x value gets closer and closer to 1, our y value appears to be getting closer and closer to 2. 1.9999 is very close to 2. So how do we write this? We say the limit of f of x as x approaches 1 from the left. Now this is how we indicate from the left. We put a little minus above the 1. And we say that that is equal to 2. All right, so this is just putting into math notation what we had already observed with this function in the previous video. So let's look at the right-hand limit. Same idea. Let's hop on the curve to the right of x equals 1 and imagine now what happens as our x coordinate approaches 1 from the right. We're moving down the curve and we are basically meeting ourselves at y equals 2 again. And you see that here in the table as x approaches 1 from above, aka from the right, y seems to be approaching 2. How do we write this? Very similar to what's above, except that it's as x approaches 1 from the right. We indicate that with a plus, and we see that it's the same value. And because it's the same value, that proves that the limit of this function as x approaches 1 overall is just equal to 2. So we establish the limit from the left is equal to the limit from the right, and that guarantees that the limit exists at that value. So the example we just looked at suggests an alternative definition of a limit, which is that the limit of a function as x approaches a exists and is equal to L if and only if two things hold. The limit from the left of a of the function exists and equals L, and of course, the limit from the right of a of the function exists and equals L. And the if and only if means that this definition goes in two directions. So if you can establish that the limit from the left and right exists and are equal, you can then conclude that the overall limit of f of x as x goes to a exists and is equal to L also, and vice versa. If you know that the limit exists of a function as x approaches a particular value, then you know that the left and right limits also exist and equal that value. So let's take that new definition of a limit and try it on a function we also were looking at in the last video. If you recall, by adding the absolute value to the numerator of the previous function, we kind of caused a break in the graph, and we can see that in the graph and the table. So for the left-hand limit, as before, hop on the curve to the left of x equals 1. So here's x equals 1. And as you hop onto the curve and as your x coordinate gets closer to 1, what do? Well, you go to the top of the mountain, over the mountain, down the mountain, and it appears that you are approaching -2. And you can see that in the table as x approaches 1, y approaches -2. Remember, y doesn't actually equal -2 here. That's just because of rounding. So how do we write this in left-hand right-hand notation, we say the limit of g of x as x approaches 1, but this time from the left, is equal to -2. Let's repeat for the right-hand limit. Hop on the curve to the right of x equals 1. Imagine what happens as your x-coordinate approaches 1. You are descending the function, and you appear to be getting closer to y-coordinate of 2. Once again, you can see this in the table. As x approaches 1 from above, y is getting closer and closer to 2. So we write this as the limit of g of x as x approaches 1 from the right, put a plus there, equals 2. And because these values don't match, according to the definition, we know that the limit of g of x as x approaches 1 does not exist. So let's get some practice with one-sided limits and using them to establish the existence of limits. And so we have this interesting looking graph, lots going on here. I'd like to actually start all the way over here to the right with what's going on at x equals 5, just because at x equals -2, I think the most interesting behavior is going on, and that takes a little more analysis. So from the left of 5, so for this first one here, if we hop on the curve to the left of 5, it appears that we're approaching y equals 2. And if we hop on the curve to the right of 5, our y-coordinate is definitely approaching 1 because this is the equation. This is the line y equals 1 right here. And because these don't match, the answers to the left and right-hand limits do not match, we say the limit does not exist as x approaches 5. All right, let's go to x equals 1. So at x equals 1, hop on the curve to the left. Appears our y-coordinate is approaching 3. Ditto from the right, 3. Therefore, we know that the limit of the function exists as x goes to 1, and the answer is 3 because these do match. Notice that f of 1 exists also. It's equal to 2, but that is not the limit. The limit is 3 because that is where the y values of the function are tending to as x approaches 1. Next, 0. So at x equals 0, approaching from the left, we're coming up the curve here. It's clear, there's no doubt about it, that we're approaching 4. From the right, we're also approaching 4. The function has no hole or gaps or breaks in it here. It's continuous. And so therefore, because these match, we can say the limit as x approaches 0 of this function is indeed 4. Finally, let's go back to x equals -2, which is right here. And let's do this one first from the right. So as we come down the function from the right of x equals -2, it's pretty clear that we're approaching 0. But what's happening from the left? You might think that you're sort of honing in on 0 from the left as well, but if you realize that this is an oscillating curve that just keeps oscillating between the values of y of -1 and 1, you don't know, as x approaches -2 from the left gets really, really close, you have no idea whether your y value is going to be 1, -1, or anything in between. So in fact, because of the oscillating motion, the limit from the left does not exist. And then so for sure, the limit of the function does not exist at x equals -2. So let's take a look at a piecewise function and thinking about limits in this setting. And why it's good to do this is we're actually, for the first time, going to work out limits without using the graph, without being reliant on the graph. So, and we're interested in what's going on at 2 because that at x equals 2 we have a change in definition in the function, and that's potentially where you might have gaps or breaks or holes in the function. So if we let's look at 2 from the left. So if x is approaching 2 from the left, that means we want x to be slightly less than 2, which means that we are going to use this definition here. So that means we can take x squared minus 1 and actually put in the value 2 for x into the left-hand branch, and we get 2 squared is 4 minus 1 is 3. And now let's look at what's happening to the right of 2. So the right of 2, we're going to be using this branch of the function. So we will plug in 2 into the function here. So we get negative 2 plus 5, which also equals 3. So without even graphing, just using left and right hand limits, we've established that the limit of this function x approaches 2 is indeed 3. And now if we pull up a graph, we can see that that's, yes, exactly what's going on. From the left of x equals 2, we are approaching, y is approaching 3, and from the right. And notice here that, yes, the function is defined, f of 2 equals negative 1, but that doesn't really relate to our limit statements.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.